45. Consider the following reaction at 298 Kelvin. So we have N2O4 gas, which will come to equilibrium, double arrow, with 2 NO2 gas, and we have a Kp of 0.142. What is the standard free energy change at this temperature? And then the next part is describe what happens to the initial system where the reactants and products are in standard state as it approaches equilibrium. So let's first answer the first question, right? What is that standard free energy change? Now remember, free energy is the same as Gibbs free energy, and the variable for that, Gibbs, G, we're searching for a delta G value. Now, since we're searching for a standard value, that means that we're just searching for a delta G notch. That little degree sign in the upper right-hand corner just means that we're using standard values. And they told us that we're at standard temp, right? Standard temp, when we're dealing with free energy, is room temp, which is 298 Kelvin. So we do have a temperature here. So now you say to yourself, okay, we have a temperature, we have a K value, right? Equilibrium constant, we're dealing with pressures, but between equilibrium constants and delta G's, there's only one formula. Now, since we're solving for delta G, it would be the easiest to memorize the equation as this, right? Delta G equals negative RT and then the ln of K, the equilibrium constant. Now, when you're using this formula, it doesn't matter what equilibrium constant you're using, whether you're using Ka, Kb, Kc, you get the hint, right? In this case, we're using a Kp value. So I'm going to plug that right on in. This has to be 0.142. Now, they already gave us the temperature in Kelvin, and for this formula, that temp needs to be in Kelvin. So this is going to be 298 Kelvin. And the reason being is all on the R value. Remember, the R value is a constant number. If we're dealing with energy values, since we are, right, delta G is an energy value, the R value is always going to be 8.314. That's a standard constant value. The units are joules per mole times Kelvin. And that's why Kelvin has to match with Kelvin. So if you can, guess, what is the unit of the delta G? Well, the R value says that the energy can only be in joules. So this value is going to be in joules. And look, we have all of our values. We have our R, T, and K. The natural log, ln, is on the calculator. So let's just plug it in. Delta G would be negative. That's in the formula. We have, let's just set this up, right? ln. We have the ln of 0.142. And then we have those two other values, R, which is 8.314, and then the temperature they told us was 298. And I can bring this in a little bit. There you go. Plug this all into the calculator one shot. The calculator will understand what's going on. So negative 8.314 times 298 times natural log, which is ln, of 0.142, close those parentheses, and then press enter. Love it. So we get a big number. That's okay because this is in joules. So we have a 4, I guess we'll do 3 sig figs, right? Because this is the final answer. So maybe I'll say 4.84 times 10 to the third. 1, 2, 3. Yep. And that's in joules. Now, they didn't specifically say whether they wanted delta G in joules or kilojoules. Standard unit is in joules. And this is standard unit is in kilojoules. And this is specifically in kilojoules per mole. So this would be in joules per mole. So if you want to just convert from joules to kilojoules, all you have to do is just divide by 1,000. Or similarly, take the decimal, move it over to the left 3 spots. I still have to put up my hands in the L's to see which one is the left. So this would be 4.84 kilojoules, or 4.84 times 10 to the third joules. delta G equals. Okay. Okay, so let's just box this answer off. That's the first answer. And now let's go to the second part. It says, describe what happens to the initial system where the reactants and products are in standard states as it approaches equilibrium. Okay, so if we maybe just pull this over here. And now if I just write this equation, right, we're saying that we have N2O4 gas. And this comes to equilibrium with 2 NO2 gas. Now they're saying, what's going on with the initial system, right? There's going to have to be some type of shift, right, as we're going to equilibrium. The question secretly is asking, are we shifting towards the product side or are we shifting towards the reactant side, right? As it approaches equilibrium with this delta G value, what's going on with my initial amounts, right? They're telling us that we have both reactants and products. So we have some values for both of these, but now as it's going to equilibrium, are we predominantly going to the products or are we going to the reactants? Well, it all comes down to what this delta G actually means. Now, keep in mind that if you have a delta G value that's positive, right, this is saying that it's non-spontaneous. It will always be represented with the K value that is less than, so I'll say less than 1. So always a delta G value that's positive will always equate to a K value that's less than 1. And both of these mean the same thing, right? A K value, an equilibrium constant of less than 1, that means that at equilibrium, as it's approaching equilibrium, in this case, your reactants are favored. So you're going to have more reactants than products. On the flip side, if your delta G was a positive value, and maybe to make this a little bit less confusing, I'm going to say delta G positive. There you go. If delta G is positive, this is the same thing as a K is less than 1. And in this case, the reactants are going to be favored. But on the flip side, if you have a delta G that's a negative, your K is greater than 1 and your products are favored. But in this case, since we have a positive delta G, we're only dealing with a K of less than 1 and the reactants are favored. So at equilibrium, you should have more reactants than products. And the reactants are on the left side. So at equilibrium, in this case, we should have more reactants because two things. K is less than 1, and you have a delta G that's a positive value. So what happens to the initial system? We need more reactants, so the overall shift is going to be, and maybe I should draw it this way, the overall shift is going to be to the left because that is the reactant side. So you're going to shift left, produce more reactants, and that's the answer for this one. What'd you think? So maybe I'll box this answer off. Okay, cool. And there's your 2 answers. So hopefully this helped. Thank you so much for viewing the video. Subscribe to the channel. Thank you for being part of this community. It's pretty awesome. You guys are awesome. We're almost at 25,000 subscribers. So thank you for all your support. We wouldn't be here without you guys. And I'll talk to you soon. Okay, bye-bye.